in this lesson, so I should say warning. Okay, so let's first talk about a metal hydride. A metal hydride has a metal component to it and a hydrogen. And that metal component is usually boron or aluminum. And that means that those metals are actually going to take on more of a positive charge. That also means that hydrogen almost is acting as an H minus. So let's think about what an H minus really is. That's a proton with 2 electrons. That's it. So he's pretty desperate to go and react with stuff. These things can be incredibly reactive. They often, or most often, need to be stored underneath extreme conditions like in oil or things like that. So you've got to be careful when using these things. NaBH4 is a very common metal hydride. Na is positively charged, which means that the BH4 in total has a negative charge to it. When reacting with an aldehyde or ketone, NaBH4 will give you an OH. Actually, this hydrogen right here is what it's specifically adding. When you add acid later is when this hydrogen appears adding. So here's the mechanism. We've got Na positive, BH4 negative. Notice how I'm trying to write that so that really this is the guy that's reacting here. And that hydrogen comes and attacks like any other nucleophile would. It goes to the center, or the carbon with the positive charge. Electrons go up, and you end up with this intermediate here that then comes and grabs a hydrogen from the acid. So you end up essentially with an alcohol right there. Because this hydrogen is not something we normally write. This is sort of how you'll see it. So these can do the reactions that alcohols can do. Okay, let's look at acyl chlorides now. So here's our acyl chloride. In this case, we're going to use 2 equivalents of NaBH4 to yield the same type of product, except that we only have 1 R group here, right? Because with an acyl chloride, you're only starting with 1 R group here. So really what we're talking about is we're talking about making a primary alcohol with acyl chlorides. So we take this and this guy, and what happens first is the hydrogen, again, comes over here. Electrons pop up. We get this negative charge here, and as electrons fall back down, the chlorine can leave, which basically reforms an aldehyde, which, when you have another equivalent of BH4, reacts just like we just saw, and that hydrogen attacks here again. Electrons go up. We end up with a negative charge right here. And in the presence of H3O+, we end up getting our primary alcohol. Okay, there are ways to make metal hydrides less reactive. Putting groups around them will certainly do that. We're about to look at a type of hydride called lithium aluminum hydride, which is lithium is your positive charge, just like your sodium was up here. Aluminum is sort of like your boron, as you see here. In this case, we've got a hydride, but we've also got 3 OT-butyl groups. So in other words, this is making it very bulky. We use this at low temperature, and now we've got a hydride that just isn't as active. So it will only react this first step, okay, so that you get this. And so it's basically going to stop right there. It just won't go through the rest of this. So there's no point in using it with a ketone or aldehyde because that's all you're going to get. Using this specific hydride, you can end up with an aldehyde. You can't end up with a ketone starting with an acyl chloride because remember, you only have 1 R group there. Okay. Okay. Next, let's talk about esters. Okay. With esters, we're going to use the full strength lithium aluminum hydride, LiAlH4. This stuff is dangerous, guys. It's very, very reactive. You're again going to follow this up by H3O+, and you're not just going to get one primary alcohol, you're going to get two. One from this R group here, and a second one from this R group here. Okay? So let's look at the mechanism. Lithium aluminum hydride, the hydride is going to go again to that carbon that's involved in the C-double bond. Electrons go up. And in this case, when they come back down, this entire OCH3 group leaves. Why? Because it can. We then will form another aldehyde, and that hydrogen comes in and things go up again. And once you reacidify, your oxygen will take a positive charge and you end up with the alcohol. The other alcohol that I wrote in here in parentheses is because of a reacidification of this leaving group right there. Again, there are ways to make a less reactive hydride that is specific to an ester. We refer to this as dibol H, which is diisopropyl something ALH right now that I can't think of. Maybe butyl aluminum hydride? I can't remember quite right now actually. And in this case, you can actually just follow this up with water because you don't have to reacidify anything. There's no H up here. And that will stop then at the aldehyde, as well as giving you an alcohol. So usually what we do is we just filter off the alcohol if it is at least liquid at room temperature. Okay. Carboxylic acids. There we go. Okay. In a carboxylic acid, we're again going to use lithium aluminum hydride, and this time we are going to get a primary alcohol. This is a little bit different because of the fact that instead of the hydrogen attacking the carbon here, it instead has a hydrogen that's acidic. And remember, H2 is a very stable type of molecule because we've got this hydrogen with a negative charge to it, and it comes and attacks this hydrogen that has a positive charge to it, making H2, so it starts bubbling out, right? And electrons go back in here, and then they flip back up. I'm sorry, I missed that arrow. And you end up with this, plus H2. That feels weird, doesn't it? It happens because of the fact that these electrons come on here, and that goes up. When you have this, we've got a negative charge right here on our oxygen. That then complexes to the aluminum that's left over, the AlH3 that's left over, which gives you another negative charge on the aluminum. And kind of this intermediate forms. And the hydrogen kind of decides to come down and touch its toes. So if you imagine, this is sort of like him doing Pilates, and he's going, oh, I'm going to go touch my toes right there. And then I'm going to kick off my foot, or kick off my shoe, okay? So that's what's happening, is that these electrons are coming down, and then that kind of flips back out. Now you've got something that looks like this. Well, we've got sort of a leaving group right here, this AlH2. So as these electrons come in, that entire thing leaves. And that's when you end up with an aldehyde. Once you have an aldehyde, okay, now things go as planned. These electrons come in here, these flip up. You once again have a negative charge, that goes and grabs a hydrogen, and you end up with your primary alcohol. That's a little bit harder of one. I would definitely suggest you run through that a couple times to make sure that you're okay with it. Okay. We're only a little bit through this. Okay, finally, amides. Probably gonna have to separate this video a little bit. Amides, we're going to use lithium aluminum hydride again, and this time we need just water. Truthfully, you can use an amide with two R groups here, but it's going to go through a different mechanism. You can also use one with NH2 here. I'm just going to show you the mechanism with the hydrogens. You end up with the same product even if you had R2, so in other words your C-double-O bond goes away, but it is a different mechanism. Depending on which one you're starting with is obviously going to tell you what you're going to end up with. Okay, again, this hydrogen can come and grab that hydrogen and make the H2 again. So when that happens, electrons come in here and they go up. So like with the carboxylic acid, these electrons will come over here and say, okay, I want to complex with you. And then he reaches down again, touches his foot, kicks off his shoe. And when that happens, we have something very similar to what we just did with the carboxylic acid. And electrons flip in. This becomes your leaving group. Okay. You've then got a C double bond to N. This hydride comes into that carbon. Electrons move that way. And you end up with that N with a negative charge to it. That can then be reacidified simply by water addition, and that means that this guy ends up with a negative, or a neutral charge, excuse me, and you end up with an OH minus, and that's how you end up with your amide right there. Okay. Now finally, there are other ways to reduce things, just like we've seen all along, things like palladium on carbon, Ronnie nickel. Any double bond here between C and N, you can reduce that with palladium on carbon and hydrogen. Ronnie nickel still does this. That's not changed. Ronnie nickel will also do, it will convert this to an OH, whether you have an aldehyde or a ketone. And just as a reminder, of course we still have the palladium on carbon, we've still got Lindlar's catalyst, but this one seems to be one that we forget more often. You end up with a transalkene if you're starting with an alkyne. If you use solid Na or Li, not charged, like zero charge to either of those, in liquid ammonia, NH3. These reactions can be very selective, and this is something that you need to work on and kind of figure out for yourself as to what's going to work where. Because NaBH4 will take down this guy all day long, but he won't touch the ester. Because remember, we need lithium aluminum hydride for that. He also will not touch a double bond, but he will give you that OH. Okay, thank you very much.